Welcome to Chemical Process Safety. This video is about flow of vapor through holes. Now, previously, we've covered flow of liquid through holes, and this is a fundamentally different situation because vapors are compressible. So before in the energy balance, we replaced the dP over rho term with just delta P over rho, and unfortunately, we cannot do that anymore. So there's a couple of classifications of flow of vapor through holes. One of them is throttling. You might have seen this in your research lab, for example. This means you are controlling the flow, such as with the regulator. And this type of process has a lot of frictional loss and very little conversion of pressure into kinetic energy. The second type of classification is free expansion. This is where gas is just allowed to flow uninhibited, and this is where most pressure is converted to kinetic energy. And this is what could propel a rocket, for example. In your fluids class, this is called isotropic expansion. Most of the time in safety, we are dealing with free expansion. So again, this is when things are unexpected, controlling the flow is probably unlikely to be the case. But you could imagine a scenario in the research lab, for example, where maybe the hose falls off of a regulator or something, and you actually are throttling while you are accidentally releasing something. But anyway, diving into the theory, so we're going to start with just the generic through any hole. So the inside situation is going to be right on the inside of the hole, inside of the vessel, and outside is going to be point 2. So just as before, the pressure at point 2 and the outside is going to be typically atmospheric. The pressure inside is going to be something. We don't necessarily know what it is, so we'll call it P0. And we'll also call the temperature inside T0. Similarly, we will define the velocity inside to be 0, and the velocity outside will be some number that we are going to try to calculate. And again, that's what we want to know. We want to know the exit velocity because that is going to enable us to calculate the exit flow rate. So for flow of just through a hole, we have no change in height. We also have no shaft work, so those terms can cancel from the energy balance. This should be a little bit higher. There we go. So this is our energy balance after we cancel stuff. Just as before, we've got this frictional term that we need to choose how we're going to deal with it. We will do the discharge coefficient thing again. All right, so this is how we define the discharge coefficient, by the way. Yeah, this is just a definition, and we will rearrange things. So how do we treat this integral of dP over rho term? The approach that we'll take is we will assume that this is an ideal gas and it is undergoing isentropic expansion. And what that allows you to say is that whatever the pressure is divided by the density to the power of gamma, that this is a constant. So gamma is a concept from thermodynamics. This is the ratio of heat capacity at constant pressure and heat capacity at constant volume. E.g. Cp over Cv. For many gases, this is going to be 1 point something. Table 4.3 in your textbook has a bunch of them. So for example, for carbon monoxide, the gamma value is 1.4. And for ammonia, it's 1.32. So it's some number that's generally a little bit greater than 1. So what this allows us to say is that because P over density to the power of gamma is constant, that means whatever pressure and whatever density that we have, remember we're dealing with the gas now, right? So density is going to be a function of pressure. We can say that whatever this is, whatever pressure and whatever density we have, this is going to be a constant. And therefore I can rearrange this and I can obtain, rearranging this one by the way, by solving for density. Density is equal to some reference density at whatever pressure times P over P naught to the 1 over gamma power. And this is what we'll substitute into the energy balance. So this form of the energy balance is slightly rearranged. I've almost solved for U2 the exit velocity. But what I have done here is I've taken 1 over rho and I've just plugged in, I've plugged this expression in there. So this is the thing that we're going to have to integrate. Don't worry, I'll show you how this is supposed to go. So in performing this integral, P naught and rho naught are both constants, so they can be pulled outside of the integral. And then we have an integral of the form 1 over x to the a power. So when you plug in the limits, you end up with this expression here. We can substitute P naught over rho naught with the ideal gas law. So because PV equals nRT, I can, it's harder to calculate what the density of a gas is. And please don't look up what the density of a gas is, because I see this all the time. If you look on engineeringtoolbox.com or something, it'll tell you the density of whatever you want to know, but they're assuming something for pressure and temperature, which isn't necessarily the case that you have. So it's better in this case to just simply substitute RT naught over the molecular weight. And this is where the ideal gas law assumption comes in. So we make that substitution, and here is our expression for exit velocity squared. Once again, we are not interested in the velocity itself. We are interested in the mass flow rate. So we need to multiply by the density and the area. Once again, recall area times velocity is volumetric flow rate. And then if I multiply that by the density, I convert the volumetric flow rate to a mass flow rate. And once again, we have this expression for density. So if I plug that in, I get this massive equation. So this is our equation for generic flow of vapor or gas through a hole. So the mass flow rate is equal to C0, which is the discharge coefficient. Again, that'll be some number between 0.61 and 1, times A, this is the area of the hole, times P naught, remember this is the pressure inside the vessel, times the square root of 2 GC, GC is the gravitational constant, 1 in SI units, or 32 in US customary units, times the molecular weight divided by RT0, and T is the temperature inside the vessel, times gamma over gamma minus 1. Gamma, remember, is a number between 1 and about 1.7 is probably the biggest one I see on the table, times the quantity of P over P naught to the power of 2 over gamma minus P over P naught to the power of gamma plus 1 over gamma. One more kind of interesting part, that a gas actually cannot flow faster than the speed of sound. And this is a very common situation. So if you recall back in the T2 video, there was a bystander who said they heard a noise that sounded like a jet engine. And if you've ever boiled tea at home, like in a tea kettle, you hear the whistle. That is vapor moving at the speed of sound. So from a safety perspective, we might be interested in knowing what the pressure ratio P over P naught is that would result in such a maximum flow where you could hear the gas actually flowing, and that's going to be the maximum. So to do this, we can take the derivative of the mass flow rate with respect to this pressure ratio and set it equal to 0. This is a very normal procedure just from calculus about how to find the maximum of a function. So we're finding the maximum value of Qm with respect to this pressure ratio. And if you do this, you would find that the pressure ratio that results in the maximum flow is 2 over gamma plus 1 to the power of gamma divided by gamma minus 1. The terminology that you'll see in the textbook and that you'll hear is choked flow, or critical flow, or sonic flow. This means, again, that the gas is flowing at the speed of sound, and this is the maximum possible velocity that it can be at. Also keep in mind that the pressures here must be absolute, not gauge pressures. In a lot of the equations that we've been doing, we have actually been using gauge pressures, which is usually frowned upon. However, in all the instances where we have gauge pressure, it arises because we have a delta P somewhere, and we're subtracting atmospheric. So that's why we're using gauge pressure, but that is not a common practice. Because this is a ratio, we definitely need to make sure that we are using absolute pressures. I mean, you can prove this to yourself, because if we put in gauge pressure for P0, we would have 1 over 0, and that's not a defined function. So let's look at a quick example. Let's say we have a leak of air to the atmosphere. And the atmosphere is 14.7 psia. That's the standard number. And it only needs an upstream pressure of 27.8 psi in order to be choked. So I get this by plugging in numbers where gamma is 1.4 for air. So by solving this, I get 0.528. What I've done here is I've rearranged this equation. I've brought P0 over to this side. And I've solved for, I'm sorry, I brought P0 over to this side, and then I brought this entire term down to this side. So I have P over this whole right-hand side. And that's how I'm obtaining a P naught, which is, again, the pressure inside the vessel of 27.8 psi in order to be choked. This is not a very large number, and therefore, again, choke conditions are common. So imagine your tire pressure, for example, is what, 34 psi, and that's gauge pressure. So the actual pressure inside your car tire is even higher than that. If your car tire were to be punctured, you would definitely hear the sound of air rushing out of that tire, indicating that the flow is choked. And if I have choked flow, there's another equation for it. So this is setting pressure equal to something. Sorry, I lost my train of thought there. So I figured it would be clear if I just went and I found the equations. This is our QM equation from before, and this is the equation for choked flow, which I just talked about. If I plug this expression for choked flow, so this part, if I plug that in for P over P naught, a lot of stuff is going to cancel and simplify. This is our equation for QM choked. So I know this derivation is a lot to go through. I typically am a proponent of going through the derivation every time that you are solving an equation, and then you'll get better at doing derivations as you go. For this one is a little bit much. So honestly, I would approach this equation as a plug and chug. If it tells you that the flow is choked, or you deduce that the flow is choked, you can simply plug in numbers to this, and this will give you what your mass flow rate is. All right, that will wrap up this video. As always, thanks for watching.